Hi, in this video I will present the phase space probability density function that comes when we just connect the characteristic function derivation to the entropy derivation. In fact, this is one of the main results of getting the two derivations mathematically equivalent. That is, let's see, in the entropy derivation we have used the, the marginal probability distribution function over a point on configuration space, which is slightly displaced from the point Q. In the characteristic function derivation, we have used the characteristic function, and if we use the relations that we have just shown to connect the two derivations, we see that these two symbols are exactly the same. That is, to take the characteristic function here is the same as to assume the marginal probability distribution function over a configuration point slightly displaced from Q. This gives us the possibility of getting, by inversion, of course, by relating these two functions, the expression for the joint probability density function upon phase space. In fact, as we can see in this side, this function is just a Gaussian and the other function is just a Fourier transform. Of course, when we invert this expression by making the inverse Fourier transform, we just get another Gaussian function, which is the expression for f. So given any quantum mechanical problem, the expression for the phase space probability density function is already defined. What the specific problem, quantum mechanical problem, will give us is the appearance of ρ, which depends, of course, on a quantum mechanical set of quantum numbers, and also the variance and the average momentum. But of course, given the solution, which is normally given in terms of psi, we can construct these three expressions and just write the expression for the probability density function upon phase space. It is obvious that we can write, from what we have already said, the average momentum in terms of the characteristic function, and also the variance, statistical variance, in terms of also the characteristic function. This is natural. The fact that we can write these two results in these terms and also the joint probability density function in this way points us towards some notion that is very akin to the central limit theorem. We will come back to this issue later on, but it's nice to stress this at this point because this is indeed an important result that reveals other aspects not only of quantum mechanics itself, but also of the role of fluctuations within its formalism. But given this expression, we are now in position to ask how specific problems will show themselves in terms of this joint probability density function. We begin obviously with the simpler problem, which is the harmonic oscillator. In this case, we give the the solution of the harmonic oscillator problem in terms of the n quantum number. This is the usual polynomial which accompanies the probability amplitude, and this is the exponential. Beta, of course, is a constant that incorporates h bar, frequency, and mass. Then, if we write our probability amplitude function in this way, we can get the phase space probability density function in a very easy way, just like this. So for n equal to 0, the first state, we get this function. For the first excited state, we get this function, and the same with the all other states. It's important to say that it's always possible to get directly the phase space distribution function whenever we get the solution of the Schrödinger equation as given here. Note also that these are somewhat complex functions, complex in the sense of difficult functions, because these functions mixes the momentum variable with the space configuration variable q. Okay, we can plot some of these functions. We plot here those that we have shown in this table here. So these plots are shown here, and for the first ground state quantum state, we have a fluctuation that has no infinities, and the probability density function upon phase space here, q and p, is just given by this equation. Note that over uh, a level curve for this function is just an ellipse, which is an ellipse given by this expression here if we make it constant. Okay, the first excited state has a different aspect, because for this state we can show that the momentum statistical moment upon configuration space has an infinity for q equal to 0, goes to infinity. This gives us the fact that the distribution now has a point here, in fact a line, in which it is equal to 0. It will be important later on for our interpretation of this kind of distribution in terms of this kind of fluctuation. This is in fact what we have to find with this entropy derivation. This repeats for higher excited levels. We have here two infinities, which correspond to the two zeros, which can say zero lines of the phase space probability density function. Here we have three infinities and three zero lines. Of course, we can do that with any quantum mechanical solution. We can do that also using the hydrogen atom. We are using these two systems because we have, of course, the expression for the solution of the Schrödinger equation, so it's easy to construct the phase space probability density function in analytical terms. Note that for the ground state we have this expression, and we have other expressions that are very complicated as we go to greater n. This c is just cosine of theta. Okay, so this is the way we get these distributions. It's very nice to see how they look like. And we can also relate our results to Bohmian equations. If we use the approach of David Bohm, we can write a Hamiltonian in the way he writes. This is just the so-called quantum potential. And if we draw, this is written for n equal to 1 of the harmonic oscillator system. So this is the quantum potential for this state. And if we draw the line, the energy, constant energy lines for this Hamiltonian, we get simply this drawing here. In the right side, we have just the level curves, that is curves of constant probability of the Liouville equation upon phase space, and we see that the two figures are quite close to one another. This means that in some sense these functions f, q, p must be some sort of exponential of these ones, but only in approximate manner, because of course here we have no assumption of fluctuations, at least not explicitly, and here we have already assumed this kind of behavior, the fluctuating behavior. So they are close to one another, but this is done only in a formal perspective. Okay, in terms of the Liouville equation, we can now use our phase space probability density to show that it satisfies the requirements of our derivation, which is it must be zero when we make the product of the momentum moments, the zero first and second momentum moments, with the Liouville equation and integrate, because this was the requirements for the derivation, the entropy derivation. Of course, we will do that using Maple, because this is a quite involved calculation. So let's go to Maple to see this happening with a specific case of the harmonic oscillator, but this can be repeated for any quantum mechanical problem we may have. Let us see. What we have here is a construction of the harmonic oscillator solution, where we have here the orthogonal polynomials These are the Hermite polynomials we have in the solution of the harmonic oscillator. This is the construction here of the probability density, and the fluctuations are constructed with in this expression here, which is just the expression we have already encountered in the previous videos, minus 1/4 of the differential of the entropy, the second order differential. So we construct, using this expression, directly the phase space probability density, and the Liouville equation, when we put in it the potential, it's just given by this difference here. Okay, after constructing these expressions, we can calculate, for instance, the probability density function for the state 0 and equal to 0. It is given by this expression here. This integral here is to show that it is normalized. And we can now calculate the Liouville equation for n equal to 0. In this case, specifically, we have that and it is already known, this result is very well known. We have the result that the Liouville equation is satisfied by the phase space probability density function. This is not true for other levels, for other states, quantum mechanical states. For instance, for the first excited state, we have this, and we can show that this calculation does not give 0 exactly. But this is not the requirements of the axiom. The requirement of the axiom is that the integrated Liouville equation over the momentum space must be 0 for the first 3 moments. So let's see if this happens. I will use here, beginning with the first excited state. Of course, for the 0th ground state, is obviously true. So let's see what happens when we calculate the various momentum moments of the Liouville equation, using the phase space distribution function that we have already derived. So this is the calculation for the first momentum moment, which is the 0th momentum moment, which is 0 because, of course, this is a positive function. So this implies that this is just 1. We have to choose this solution here. We may calculate this for the first momentum. It is also 0 for the same reasons, and the second is also 0. Note that if we put here the third statistical momentum moment, this is not 0 anymore. This has a term here which is always not 0, and this means that the Liouville equation is not satisfied for greater momentum moments. We can also do the same calculations, for instance, for the second state, the excited state. It's possible to show that again this function is identically positive. Look at the graphic, it's plot here. Note that the function is always positive, so we have this 0 as a solution. So the second moment, the first moment, and the 0th momentum moment are all zero for the same reason. For the same reason here. Okay. This can be shown for any state. We can show, for instance, for 5, the fifth momentum state. Of course, this expression is brutal. It's very difficult to represent it, but it has the same behavior of the previous results. This function can be shown to be positive for any value of x, and so the result is that this is the result that we have to assume. The same for the other two moments for the same reason, but for the third moment, again, this will give a non-zero expression. Okay. Now we can use the phase space probability density function, which is here, to show that the energy that we get is exactly the same energy that we get for the harmonic oscillator problem if we substitute the underlying probability density function over phase space. For instance, if we put here the ground state, our energy is just half, which is the usual result. Of course, we are using the units of h bar equal to 1, omega is equal to 1, and the mass equal to 1. In some sense, something like atomic units. For the first excited state, we have the result, and this repeats itself for any state that we substitute here. Calculations, of course, gets somewhat more involved, but the results we can get, sometimes Maple is not able to do that, but the results can be shown with some modifications here, that the results is always the result we expect for the harmonic oscillator problem. Here Maple is not being able to find the result, but at least up to 3 it is easy to show this result. Maybe I can try to calculate this numerically to see that this in fact is the result we would like to have. Okay. See, now it's possible to show the results. Let's do only one more here, and in fact we have all the results we want to get. Okay, this is what we want to show. So we have just shown using Maple that we have this requirement for the entropy derivation exactly satisfied by the phase space probability density function that we have just found. In the next video, we will show how to calculate some average values using this function. We have already shown this in some sense, but we will show how to calculate the Heisenberg relations using the first axiom that we have presented. Thanks for watching.